Okay, so in this lecture, what we want to discuss is a center of mass. You probably have seen it in your other classes, discussing it, and maybe even in high school classes. Finding center of mass, and maybe you didn't use the methods that we're going to teach you here, but you have discussed it based on some regular shapes or for some regular shapes. So we're just going to build up on that understanding and that intuition, and we're going to throw in some calculus methods to help you find center of mass of some other shapes. The idea is basically very simple. It's a concept that goes back to your time in the playground. If you had two sides of a seesaw, and if one side was heavier than the other side, of course, you would see that the heavier side would tilt the balance, and you would have the seesaw. One person would go down, one person would go higher. So that would be the idea. And of course, again, that's because the arms are the same length. The idea here is if you have a heavier side, then to balance it, you would have to move your fulcrum closer to the heavier side, and that will balance. And that's intuition, right? You will feel like, well, if I have a heavier mass and then have a lighter mass and I want to balance it, then I would probably have to put my fulcrum closer to the heavier mass. So basically, you get a balance if the product of your mass times the distance from fulcrum is equal to mass times distance, second distance from the fulcrum. That's how you create the balance. So as long as m1d1 is equal to m2d2, then you have a balanced system. That's intuition, and that's something that we've seen. You can experience it yourself. Now the question here is, how can I use this in finding center of mass? So let's make things a little bit more formal. Suppose I have two masses, say m1 and m2, that are not equal. And I want to find it somewhere in between where I will have the situation that I would have like a stable system or equilibrium. Let's call this x bar. So m1 is at x1 place, m2 is at x2 place, and x bar would be what would be a center of mass. If I had a bar going from here to here, that would be creating a center of mass there. So the distance from x bar to x2 would be x2 minus x bar. The distance from x bar to x1 is x bar minus x1. And the idea here is that m1 times x bar minus x1 should be equal to m2 times x2 minus x bar. Or m1 x bar minus m1 x1 would have to be m2 x2 minus m2 x bar. Solving for x bar, take this to the other side, take this to the other side, you get m1 x bar plus m2 x bar is equal to m1 x1 plus m2 x2, or m1 plus m2 x bar is equal to m1 x1 plus m2 x2. X bar, which is what you're looking for, is m1 x1 plus m2 x2 over m1 plus m2. This is your total mass. And this is what we refer to as a moment. Basically, if I calculate the sum of products of mass times distance of the masses from some fixed location, then that would give me the moment. So it's a moment about the origin in this case, where you're calculating the distances from the origin. Okay, so a moment about the origin, first moment about the origin over total mass gives you your x bar. A relatively simple idea. If I had more masses, then I would just keep doing that for total masses. But in this case, I only have two masses. And I'm trying to find the center mass for those. Your book discusses having masses in different places of the plane and trying to find the center of mass of those objects. But those multiple masses. So now let's bring in the calculus in this, understanding that this is what we're going to have to do more or less. Let's bring in the calculus in this. Suppose I have a shape, again, the same shape that I've drawn many times, like the same eyebrow, and I want to find the center of mass of this shape. First thing that I'm going to make it a requirement for this is that this shape has a constant density. So rho, which is usually it's a Greek letter RHO, a Greek letter, rho is a density, represents a density, and suppose the rho is some constant. Now suppose the function that I have here is y equal to f of x, and boundaries are a to b. So I need two things. I need x bar and I need y bar. X bar would be somewhere in the horizontal direction, y bar would be somewhere in the vertical direction. So I'm looking for some center of the, I'm looking for the center of mass of this object, this lamina. So let's talk about x bar first. So I do the same thing I did before. I'm going to slice it. This is the partitioning process has been happening a lot. And I'm going to, each of those, I can flatten them out by whatever convention, whatever way that I want to flatten it, midpoint, left point, right point, whatever. And after flattening them, each of these is going to have a total mass, which I can use by multiplying the area times density. So each of those is going to have a total mass. So to calculate the mass, I can just multiply rho times fxi star delta x. This is going to give you the area of each rectangle. Fxi star is the height for each rectangle. Multiply by the density, and you get the mass for each of the rectangles. So the total mass would be exactly limit as delta x goes to 0, a sum I equal to 1 to n, again, rho fxi star x, which is integral language. It will be integral from a to b of rho f of x dx. That's your mass. Remember that the total mass goes at the denominator. Okay, very well. Now for moment, what I have to do is I have to multiply mass by distance. The problem is, how am I going to figure out what the distance is and what the mass is for each of those? So what I can do is, for a moment about the y-axis, I can assume that I'm going to place my masses in the middle of each of these rectangles. And the distance of each of those masses would be the xi stars. This is x1 star, this will be x2 star, and so forth. So for each rectangle, if I want to calculate moment about the y-axis, it's going to be sum of multiplying the distance, which is xi star, times the mass of each box, which is rho f of xi star delta x, and adding them above. Again, taking the limit, n goes to infinity, or delta x goes to 0 of this. And remember that the integral language for that would be a to b rho x rho f of xi, or f of x now, sorry, dx. knowing rho is a constant. This. So my x bar, which is moment about the y-axis over total mass, is going to be rho a to b x f of x dx over rho a to b f of x dx, where rho's cancel out. We end up with this. Relatively straight calculations. It does help that rho is a constant, because then you can pull it out and cancel it. If rho was not a constant, you couldn't do that. And these calculations, this setup wouldn't work very well for that. Now, for y bar, I need to find the distance of each of those with respect to the y-axis, multiplying and so forth. And if you remember, I put the masses halfway in between. So what I can do is, for y bar, I need mx. And mx would be equal to approximately sum I equal to 1 to n. For my distance, I use the representative points. So it's half of fx I star. If this is fx I star, half of it would be the distance from the x-axis. Then I multiply it by mass of it, rho fxi star delta x. So that's the density, that's the area. Area times density gives you mass, mass times the distance, and adding them all up. So if I calculate mx, it will be exactly limit as n goes to infinity or delta x goes to 0 of this summation, which I can write it as fxi star square, because I have two instances of it, rho delta x, or in an integral language, a to b rho 1/2 fx squared dx. And then my y bar, which is mx over m, would be 1/2 rho a to b fx squared dx over rho a to b fx dx. So it's going to be 1/2 if the rows cancel out, a to b fx dx, a to b fx squared dx. So that's where the formulas come in that you use for center of mass. A classic example for this would be center of mass of a half circle, which is located at the origin. And suppose the radius is 2. And I want to know what the center of mass is. First of all, and the density is constant. As you notice, the rho doesn't really play a role in either of the formulas because it's a constant density and cancels out in both cases. You would revisit this idea in Math 1D, and in there, your density is no longer constant. The formulas look slightly different, but they're consistent. So first, my mass, my x bar, is going to be integral from a to b of x f of x dx over a to b of f of x dx. And notice this is just the area of the object. So I don't actually have to integrate for the bottom. I can say if it's a half circle, circle is pi r squared for the area, and the radius in this case is 2. So that would be the area of the full circle. So if half a circle would be half of that. So I can just write that. I don't have to integrate. You could integrate if the shape is not as friendly, you could integrate, but you don't have to if it is a nice shape. But for the top integral, you really have no choice. I have to find an equation of this half circle, and the equation of circle is x squared plus y squared is equal to r squared, which in this case is 2 squared or 4. Then y would be square root of 4 minus x squared. And I don't need the plus or minus because it's the top half of the circle. So it's going to be negative 2 to 2, x square root of 4 minus x squared. So x comes from this, and f of x is 4 minus x squared dx. That requires an integration using substitution. So I let u be 4 minus x squared, du is negative 2x dx. So negative 1/2 u to the 1/2 du. X dx is negative 1/2 du. This is u. When x is negative 2, negative 2 squared is 4. 4 minus 4, sorry, is 0. When x is 2, 4 minus 4 again is 0. So my x bar turns out to be 0. Is that consistent with the shape that I have? Yeah, it's symmetric. So, and the density is constant. So my center of mass would have to be on the y-axis, or my x bar would have to be 0. Not too bad. It's good when things stay consistent and you can verify them with the picture. Now, y bar. Could you have done that on the test? Could you have just looked at it symmetrically and say, well, center mass would have to be at least have this x bar? Yes, but you have to be sure about it. Sometimes pictures could be deceiving. And of course, when you go to the higher level, when you go to Math 1B, that is not a very simple thing to verify. So sometimes the symmetries are not very easy to recognize. Shapes could be deceiving. For y bar, once again, my denominator is the area. The numerator is 1/2 integral from a to b of f of x squared dx. So you get 4 pi in the denominator, the 1/2 and 2 gives you 4 pi. Negative 2 to 2 of 4 minus x squared dx. 4x minus 1/3 x cubed from negative 2 to 2. 8 minus 8/3, if I plug in the 2, plus 8. So again, go through the process. You have 1/2 integral from negative 2 to 2 of square root of 4 minus x squared, which is your function, squared, over 2 pi. Integral negative 2 to 2 of 4 minus x squared dx over 4 pi, because the 1/2 and 2 pi equals to 4 pi. And the derivative of 4 is 4x, and the derivative of x squared is 1/3 x cubed. You go from negative 2 to 2. You could also, because it's an even function, you could go from 0 to 2 and double it if the calculation becomes easier. In fact, let's do that. So it became a little bit easier calculations and less room for error. So I double this and I go from 0 to 2. So I get 4 times 2 is 8 minus 8/3 over 4 pi. 8 minus 8/3 is 2 and 4 pi cancel out. 8 minus 8/3 is 24 minus 8 is 16/3 or 8 over 3 pi. So that's going to be my y bar. And if the center of mass or centroid is x bar, y bar, x bar is 0 and y bar is 8 over 3 pi. Now notice the halfway point here is 2, right? And 1, right? 8 over 3 pi is about over 9, right? 3 times 3.14, it's over 9. 8 over something that's like 9 or above, it's less than 1. So your center mass is actually going to be here somewhere. It's consistent with the picture as well because you have more weight at the bottom half than you have in the top half. So your center mass should be pulled towards the heavier side more. So you have more weight at the bottom, so your center mass will be closer to the x-axis, closer than the halfway point. So that's how you find center of mass. In general, center of mass is not too difficult if you follow the formulas. And the shapes are usually within the shapes you've been dealing with from 6.1, the areas between the curve section. The only thing that you have to be careful about is sometimes you want to calculate the center of mass where your area, the region, is between two functions, f and g. As you would expect, x bar doesn't change because again, you're just doing the difference between them. So for the x bar, you still get the 1 over area of integral from a to b for your moment is x times f of x minus g of x dx. That's what you would expect. Because your height now is going to be f minus g, your width is going to be delta x, so that's this part. The rho cancels out with the rho at the bottom, and then x times that is your x bar away. For y bar, to calculate the center of mass, it's actually going to be slightly different because you have two things to worry about. You have two things to worry about. So if I were to derive for this my y bar, of course, my average value or the midpoint would be f of x minus g of x divided plus g of x divided by 2. So the distance I'm going to use is going to be f of x plus g of x divided by 2. So that's the distance I'm going to use. Then I multiply that by the mass of that, which is f of x minus g of x delta x, and of course there is a rho. So if I'm trying to calculate mx, it's going to be rho times this is the area times rho gives you mass. This is the distance I'm going to use, which is going to give me sum over I of f of x plus g of x times f of x minus g of x is f of x squared minus g of x. That's a difference of squares formula, right? Delta x. So for y bar is actually going to be 1 over 2 integral from a to b fx squared minus gx squared dx. So the formula is slightly different. Some students think it will be f of x minus g of x quantity square, but as you can see through the derivation, it's actually because of the difference of squares you get one that is the difference of squares of the two functions for that. So if I use, for my example, if I use the two functions y equal to x squared and y equal to x cubed, of course, x cubed goes slightly below x squared between 0 and 1, and x squared is above. Because between 0 and 1, when you take it to the higher power, you actually get something smaller. Mass, well, if I just write the formulas for x bar and y bar, x bar would be integral from 0 to 1 x f of x minus g of x dx over integral from 0 to 1 x squared minus, that's going to be playing the role of your a dx. So it's going to be 0 to 1 x cubed minus x to the 4 dx over 0 to 1 x squared minus x cubed dx. So 1/4 x to the 4 minus 1/5 x to the 5th from 0 to 1. 1/3 x cubed minus 1/4 x to the 4 from 0 to 1. 1/5 minus 1/4 minus 1/5. 1/3 minus 1/4. You have 1/20th over 1/12, 12/20th or 3/5. That's going to be my x bar. Okay. My y bar is 1/2. Now the bottom doesn't change. Bottom is still going to be 1/20th. 1/12. That's the area. 1/2 0 to 1 fx squared minus gx squared. Which is going to be 1/2 and 1/12 gives you 1/6 in the denominator. X to the 4 is 1/5 x to the 5th minus 1/7 x to the 7th. 0 to 1. 1/5 minus 1/7 over 1/6 is 2/35 over 1/6, which is 12/35. That's going to be your center of mass. Is going to be x bar comma y bar. That's your centroid or center of mass. Is 3/5 comma 12/35. Okay. So that's the concept of center of mass. That's the only thing from section 8.3 that I hold you responsible for and you need to know. I will post another lecture on probabilities from 8.5. So you guys can look forward to that one. 8.4 is some other applications you can review if you wanted to, but that's not going to be part of your test. And the first part of 8.3, since we did the work with the tank problem and so forth, then I don't have to do the first portion, which is this 8.3 involving hydrostatic force and so forth. But if you want to read them and if you have any questions about it, I'll be happy to help you. If you saw it somewhere and you want to know more information about it. Other than that, this is all you need to know from 8.3, and I hope this helps you to do some of the problems. Once again, if you have any questions, you want to do those problems in the recordings, please let me know. Thank you.